I wanted to make a video to explain this homework set because for some of you who came to office hours and really watched all those videos, you put it together nicely. And for others of you who didn't have the chance to come see me, it seems like you're still putting some of these concepts together. So I wanted to review this homework set and just show you functionally how to solve these MO diagram problems. So the first one, we had a complicated molecule, formaldehyde, more complicated than I had put in any of our asynchronous lectures. So the first thing you needed to do was to draw that molecule as a Lewis structure. So here's the Lewis structure of formaldehyde. It might help to assign hybridization of any of those atoms. Think about the types of bonds that are involved in those atoms. And then think about what molecular orbitals would need to be built to construct that molecule. Okay, so just a reminder on how we get hybridization. This carbon has a steric number of 3 atoms are attached and no lone pairs. So a steric number of 3 means we need 3 hybrid orbitals around that carbon. And so that means that carbon itself is sp2 hybridized. When carbon adopts sp2 hybridization, we make 3 new sp2 hybridized orbitals, and we have 1 p orbital that's left unhybridized that's used to form the pi bond in this molecule. For oxygen, I have 1 atom attached and 2 lone pairs, so also a steric number of 3. So that oxygen is also sp2 hybridized. What do those hybrid orbitals hold? They hold the non-bonding electrons, and hybrid orbitals are also used to form a sigma bond. I feel like I'm making this picture too complicated by drawing that. Let me just list what types of bonds there are in this molecule. So maybe if you didn't do so before you tried to solve this problem, pause the video and do it now. What types of bonds are present in this molecule? Well, I have 2 sigma carbon-hydrogen bonds formed by the sp2 orbitals on carbon overlapping with the s orbitals on hydrogen. I also have 1 sigma carbon-oxygen bond where the sp2 orbital of carbon is overlapping with the sp2 orbital of oxygen. There are a total of 4 bonds in this molecule, so far I've listed 3. The remaining bond is a pi bond between carbon and oxygen. And remember, pi bonds are formed by overlapping p orbitals. There are still some more valence electrons. There's a total of 10 valence electrons in this picture. The other 2 are lone pairs on that oxygen that are in oxygen's sp2 orbitals. So the question was, which of these energy level diagrams could match that molecule? Well, a total of 4 bonds. Well, when I look at these molecules, the middle of any MO diagram is considered to be energy equal to 0. So neither stabilized as a bonding interaction nor destabilized as a non-bonding interaction. And each of my options, let me use a different color, had 2 orbitals at this level. That would be where your non-bonding orbitals come, is that energy equal to 0 or equivalent to the non-bonding electrons. Well, this molecule has 2 lone pairs. So that doesn't help me eliminate any of these options. Still, all 3 could be options. Now I have 4 overall bonding interactions. Well, bonding orbitals come below energy level of 0. So for diagram A, I have 4 bonding interactions. For diagram B, I have 4 bonding interactions. For diagram C, I have 5 bonding interactions. So I can eliminate diagram C. There are too many bonding orbitals. too many bonding orbitals. Well, that leaves me diagrams A and B. So now which one of these types of bonds, sigma or pi, should be more stabilizing? Hopefully you answered to yourself, sigma. Sigma bonds are on that axis of bonding. They are more stabilizing than pi bonds, which are around the axis of bonding. And so the pi bond would be the least stabilizing. I should have one orbital in the level right below E equals 0. And I see that for both of these diagrams, I have that type of situation. I have one type of bonding orbital that's lower in energy than non-bonding, but close to the non-bonding. So that would be my CO pi bond. Well, that means that the level right above would be my pi star CO. Well, still, I can't eliminate either of these diagrams. They could still both be the correct answer. So let's think about the remaining bond types. I have one sigma bond that's CO, and I have two sigma bonds that are CH. Here I have two bonding orbitals and one bonding orbitals, one bonding orbital and two bonding orbitals. The truth of the matter is, based on your level of knowledge in Chem 120, A or B could be correct. I don't expect you to know which is more stabilizing, carbon-hydrogen or carbon-oxygen at this point, nor will I expect you to know it for this class. All I was looking for was a logical process of how to solve for the diagram. So I would have accepted the labels of sigma CH, sigma star CH, and sigma CO, sigma star CO, just as easily as I would have accepted sigma CH, sigma CO, sigma star CO, sigma star CH. Both of those were accepted for full credit. This molecule has 10 valence electrons in it. 2, 4, 6, 8, 10, 12. Sorry. Yeah, sorry, 12 valence electrons in it. So if I were to put electrons in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Both of those would be viable options for that molecule. Okay, for the second problem, anytime you want to build an MO diagram, you need to start with the Lewis structure. So the Lewis structure for carbon dioxide looks like this. And if I were to assign hybridization, the oxygen atom has one atom attached and two lone pairs, so a steric number of 3. So that's sp2 hybridized oxygen. And the carbon is attached to 2 atoms, has no lone pairs, so a steric number of 2. So carbon is sp hybridized. Now, what does sp hybridized carbon look like? I make 2 sp hybridized orbitals. I have 2 non-hybridized p orbitals. Overall, carbon has 4 valence electrons. So 1, 2, 3, 4. These are going to be used to form any pi bonds. These are going to be used to form sigma bonds. So we use the hybrid orbitals to form sigma bonds. We use the unhybridized p orbitals to overlap and form pi bonds. What does sp2 hybridized oxygen look like? When we have sp2 hybridization, we form 3 hybrid orbitals. And we have 1 p orbital that's not hybridized. Oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Okay, well, right here, I see that we have 2 lone pairs on oxygen. And we see that in our Lewis structure. Here we have two lone pairs that are going to be living in a hybrid orbital. But then I also have the need to form a sigma bond and a pi bond. And so here in my molecule, I see I have a double bond, which is a sigma bond and a pi bond. But guess what? This molecule has two oxygen atoms. So you really have twice this number of available orbitals because you have two oxygen atoms. In other words, I have another p orbital with an electron in it, and I have another 3 sp2 orbitals. Two of them hold lone pairs, and one of them has a bond, an orbital ready to form a sigma bond. Okay, well, now we're ready to make our diagram. I'm going to clean this up a little bit because I don't like what I drew there. Here's my two lone pairs, and here's my other half-filled sp2 orbital. Okay, well, the easiest thing first, those lone pairs don't change in energy. My non-bonding orbitals, there are 4 of them, and they are at the same energy as the atomic orbitals that they came from. So these are the oxygen sp2 orbitals. That's where the 4 non-bonding electrons in my molecule live. Okay, well, now we're going to form some bonds. Which is more stabilizing, sigma or pi? Still sigma. What forms the sigma bonds? Hybrid orbitals. So the carbon sp orbitals are going to overlap with the oxygen sp2 orbitals to form 2 sigma carbon oxygen orbitals. If we form a sigma, we must also form a sigma star at equal and opposite energy. So again, those hybrid orbitals are going to overlap to form the sigma star. All that's left is our p orbitals, which are going to overlap to form our pi bonds. Again, we're forming 2 pi orbitals between carbon p and oxygen p, which means we also form 2 pi star between carbon and oxygen. Lastly, I need to put in my remaining valence electrons. In this picture, I have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons in my picture. Lastly, I want to assign a bond order. Well, bond order, we add up all the bonding electrons, 2, 4, 6, 8, minus the bonding, anti-bonding electrons, which are none, divided by 2 means we get a bond order of 4, which seems silly because we don't have a 4 bond. Instead, we have 2 double bonds. So we have 2 different equivalent bond types. So the bond order for each of those bonds is 2. A bond order of 2 equals a double bond. Okay, last one, maybe trickiest one. Doing the same process, but for cyanide as the anion. So here's my Lewis structure for cyanide. Carbon has 1 atom attached plus 1 lone pair, which gives it a steric number of 2. So sp hybridization. Nitrogen has 1 atom attached and 1 lone pair, so a steric number of 2. So also sp hybridization. What does sp hybridization look like? I have 2 sp orbitals. I have 2 p orbitals. Now, nitrogen carbon has 4 electrons naturally. 1, 2, 3, 4. Nitrogen has 5 electrons naturally. 1, 2, 3, 4, 5. Now this is a negatively charged species, so one atom has more electrons than it normally has. Since we see there's a lone pair on carbon, I'm going to go ahead and put that lone pair in an sp orbital because that lone pairs live in hybrid orbitals. Okay, so in constructing my diagram, I know that non-bonding electrons are at the same energy as they were on the atom that they are found on. In other words, I have a non-bonding lone pair from carbon's sp orbital, and I have a non-bonding lone pair from nitrogen's sp orbital. So this is kind of unusual. We have different energies of non-bonding electrons, but that's okay because the atoms themselves have different relative energies. So those non-bonding electrons are neither stabilized nor destabilized. They are found at the energy of those relative atoms. Okay, well, in this species, we have 1 sigma bond and 2 pi bonds. Well, we know the sigma is more stabilizing. So we're going to mix the hybrid orbitals to form our sigma bond, sigma carbon nitrogen sp. And we're going to mix our p orbitals to form our pi bonds. We have 2 pi bonds between carbon and nitrogen overlapping p orbitals. And if we mix to form a bonding interaction, we must also mix to form an anti-bonding interaction. So we make pi star orbitals. And we make sigma star orbitals. Now we have 2, 4, 6, 8, 10 electrons in this picture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in our picture. That's it. Bond order, we calculate by the number of electrons in bonding orbitals, 2, 4, 6, minus the number of electrons in anti-bonding orbitals, 0, equals 6 over 2, which equals 3, which means triple bond, which is exactly what we see in the picture, a triple bond. So that corresponds to the bond order we would predict from our MO diagram. I hope this was helpful and helped you walk through 3 more examples of these types of problems to get you a few more skills. See you soon.